Welcome back. We're going to talk a little bit about, again, light, and I'm going to remind you of quantum theory. Max Planck came up with the idea that energy comes in only certain allowable energy levels, kind of like coins come in only certain currencies, penny, nickel, dime, quarter, there's no 14-cent piece. And what he observed was when hot objects, when they get hot, they start to glow and give off light. When it's a little warm, it might be red and then orange and then blue, and then it gets white hot. Well, if you continue to add energy, it should actually go to ultraviolet, and that didn't happen. Now, that was a curious thing. He called it the ultraviolet catastrophe. You can read more about that. I probably won't ask anything on my test about that. But from these observations, he concluded that energy is emitted in these very small, specific quantities called quanta. And we would think of these as little photons of energy. And a quantum is the minimum amount of energy change. So if we're looking at, here's an atom, let me hide this here. If we're looking at an atom of hydrogen, you've got the nucleus here and you've got electron energy levels that the electron can be in. Those are the possible electron orbits that the electron can be in. And the electron can be here or here, but somehow it spends no time in between, right? So it just jumps, you see it jump from the second to the third and spent no time in between. That's a quantum idea. I don't know how it happens. That's just the idea of the theory. So what does this whole continuous versus quantized energy mean? Well, you see here, this is continuous energy. You can keep applying energy and it goes up, 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 and you can stop anywhere you want on the left. On the right, there's only certain allowable stopping points here, 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 and here. And we believe in the atom, the energy is quantized, kind of like ladders, rungs on a ladder, right? Where you can't stop halfway. Either on the bottom rung, the first rung, the second, or the third, but you're not in halfway between one. Let me give you that another way. Let's look at these two ramps. I'm going to put a little ball on here, and I'm going to have you blow from the right toward the left. Ready? Oh, that didn't work. Let's try it again. Blow. And there it goes. And the ball rolls right down the ramp. Notice it wasn't going to stop anywhere on that ramp. Now let's repeat it this time, and we're going to use the steps. Go ahead and blow, go. And notice when you blow, the ball goes down. You blew too hard. Let's try that one more time. All right, put the ball back. Now don't blow quite so hard this time. Ready? Go. Oh, that was much better. See how that time the ball stopped halfway? It stopped on one of those steps. So on the right side, energy is quantized. It has to stop on one of these steps. And on this side, it's continuous. It doesn't stop at all. So classical theory would have described energy as being continuous. But Planck said it's not going to be continuous. It's going to be quantized. And quantum theory suggests there's only certain steps of energy that are allowed. Now, let me give you an example of this. Albert Einstein won his Nobel Prize for figuring out the photoelectric effect, not for relativity or any of that stuff that people might talk about, but the photoelectric effect. Now, if you have a solar calculator, you know the photoelectric effect. It's how your solar calculator works. Now, let me explain it to you. Well, I'll explain in a second. Let me skip all this slide because we've done that. Uh-oh, these are my Star Trek slides. How'd they get in here? No, they're not. They're talking a little bit about what is a photon, because sometimes on Star Trek they talk about fire the photon torpedoes. Well, a photon is a bundle of energy. It's actually a really, really tiny bundle of energy. So if they were shooting photon torpedoes at you, they probably weren't very powerful. Now, let's pretend that we are going to be shining light on metal plates. So I've got a bright red light, and I'm going to shine it on this metal plate. And when I do that, it looks red, but no electrons are kicked off the metal plate. If, though, I take and do the same experiment, this time with a dim blue light or even an ultraviolet light, and I shine it on the metal plate, now electrons are kicked off. So The dim blue light is enough energy to cause ionization of the metal. When metals, remember, metals want to lose electrons to form cations. When they do that, if you can capture the flow of electrons, you have electricity. Now, this works equally well in the dark. Red light on metal just makes it look red, no electrons emitted. And if you take dim blue light or ultraviolet light and shine it, electrons are kicked off. Now, think about this is what happens in the dark. So in black and white photography, you're in a dark room, you have a red light, and the red light can show on your photographic paper. The photographic paper actually has been coated with a silver halide material. So there's actually silver metal on the paper. Red light doesn't really affect the paper. But if you turn on white light, and even for a short period of time, when it hits it, it's going to kick off electrons and expose the paper. So if you put a negative in between here, an image is formed. Then when you process it, you get a picture of my three children many years ago getting ready for Halloween. My daughter was dressed as a doctor, and that's what she currently is doing. She's finishing up medical school right now. She's going to start her residency next year. This is my son, Peter. He's a senior. And this is my son, who's a chemical engineer. All right, let's keep moving. If we were in class and had the ability, we would do a little stuff with photography. But again, with COVID, we're not going to be able to do that this year. So I'm going to skip this slide as well. Now, how does this all relate? Well, light we can think of as maybe paint. So imagine this. If I were to take, I got two identical paint cans, and I got this one a little bit farther away from this wall, and this one a little bit closer. I said that backwards, but you know what I'm saying. Now, I'm going to squeeze those triggers, and I'm going to start painting. Here we go. And I run out of paint. Now, I apply the same amount of paint on the left and on the right, but it looks brighter on the left, doesn't it? Excuse me. Same amount of paint was applied to both surfaces. Now, instead of using paint, let's paint with light. If I spray light on these two surfaces, it's the same amount of light came out of my, maybe a flashlight, right? But it looks brighter here because it's spread over a shorter distance. Light spreads out by the square of its distance. So if you're twice as far away, you actually see 1 over 2 squared, or 1/4 the amount of light. So as you go out, right, we'll call that our base, 1 time. You go twice as far away, you see a 1/4, 3 times, 1 over 3 squared, a 1/9, and so on. So that if this was radiation in the form of nuclear radiation, if there was a leak, the most important thing for you to do is get as far away from it as you can. If you're 5 times farther away than somebody else, you get 1/25 the amount of radiation they get. Now, the photoelectric effect is, I'm going to explain it this way. We have a light source here, and I've got metal down here. Now, the metals, remember, the blue here represents the cations, and they're cations because metals don't like electrons, and they tossed off the electrons. That's the little orange things. So I've got a sea of electrons floating around here. And when the light strikes the metal surface, electrons can be ejected, okay? If you have more light, more electrons will be ejected. Hopefully that makes sense, right? Twice as much light, twice as many electrons going to get kicked off. Now, if you have a higher frequency light, like green, than red, the electrons are going to be ejected at a faster rate. Now, I'm going to skip this and go, well, we already did our little darkroom analogy, so I'm not going to go there. We can kind of look at it. If I use red light in a darkroom, the red light hits and not a darn thing happens. I maybe would have liked that electron to leave, but it wasn't coming off with the red light. If I try it with a green light, then I notice that when it hits, the electron is indeed kicked off, so my film would be exposed. That's why red lights are used in dark rooms. If I have more light, I'm going to find out that more electrons are kicked off. In other words, the longer I expose my paper, the darker it's going to get. Now, if you use really high frequency light, it happens really, really fast. Those electrons are leaving. Okay. Now, white light is all the colors of the rainbow, so generally we don't use a green light or purple. We just use a white light to expose the paper. Now, your calculator, this part right up here, there's metal behind there, and when light hits it, it is going to be a photoelectric generator. So if I could look inside here, I've misfrizzled this, you have here a metal surface, and it's been encased in this evacuated chamber. When sunlight, radiant energy, or even room light hits the metal, it kicks electrons off because it's ionizing to the metal surface. The electrons have a negative charge. They're attracted to the positive terminal, and it creates a voltage that then runs your calculator. So as long as there's light there, that calculator will run. Some of you have noticed that if the teacher has most of the room lights on, some of those calculators are a little bit hard to make operate. Right? You got to kind of move toward a window or something else. All right. We can kind of think about photoelectric effect and frequency. I've got my light source. I'm going to pass it through a lens and then a slit and then a prism. And so there's the light, goes through a lens, through a slit, and that white light turns into the rainbow. Now, certain metals will kick off different wavelengths of light because what we have to understand is the atom has like a unique fingerprint, a unique electron configuration where the electrons are in the atom. And they can become excited, jump from the ground state up to an excited state. And then when they fall back down, when no more energy is stimulating them, then they will release that energy and it will be unique to each element. Okay? We can see this happen in the dark. It's really the same slide with a black background. All right. Now, Einstein says that light is both wave and particle. Lots of people have said that. A photon, we've already used that term, is a certain amount, a bundle of energy. They come in different sizes. The bigger, more energetic photon is the higher frequency of light. So violet light would be higher energy than, say, red light. And we went through those calculations, C equals F lambda, E equals H nu as well. We already gone through that calculation. I think, maybe not. Let's go through this one. All right. So find the energy of a red photon that has this frequency. So we want the energy, that'll be in joules. We know the frequency. Now this person's using nu. We generally use F for frequency, but it's given 4.57 times 10 to the 14th hertz. And we know that's the frequency because it's in hertz. And we know Planck's constant, this never changes, 6.6 times 10 to the negative 34th joules per second. So our work for this, E equals HF or H nu. So we know H, we know nu. We simply multiply those two together. Now a hertz is a cycle per second, and then that's going to take care of this second here. So that will cancel, and we'll be left with units of joules. So the math on this, when you multiply it, you get 3.03 times 10 to the negative 19th joules of energy. All right, you've got some light problems to work on for sure. I'm going to stop this video and then I will make another one so that it'll chunk up a little bit nicer for you. All right, thanks for listening and take care of yourself, and we'll talk a little bit later. Bye.